So hello everyone. I'm joined today by Moritz, who's going to talk to us about a very interesting code, which I'm sure you've seen, FluidX3D. So welcome, Moritz.
Hi, nice to meet you, Val. I'm on the internet.
Yes, yeah, we're on the internet. And indeed, I have up the code here in Visual Studio. So FluidX3D, very nice fluid simulation code. I should tell everyone the reason that I found this, the reason I invited Moritz on is I've been teaching students, I've been teaching them about GPU programming, whether it's for games or for academic sort of CS kind of and physics and that sort of thing. And I found this as a great example. We looked at this with my students, had fun running it, as I'm sure you would if you give it a try. We have the code in the description, so go ahead and download it, or you pull it off GitHub. Let's go through and we'll just run a test, and then we'll jump into your slides, find out more about you, Moritz, if that's okay.
Yeah, sure.
So my suggestion, if you open it up, you'll need defines.hpp and setup.cpp. You'll tell me if I'm doing something horribly wrong, Moritz.
I see it only with a bit of delay.
Yes, there's a bit of a lag. But what I'm going to do is so this is the setup. I'm going to scroll down to find the cylinder in a rectangular duct case. And I will just uncomment that. So we have a little case that we're going to run here. That's in setup.cpp. And we'll go into defines.hpp. We'll need to know it tells us that we need to enable volume force and interactive graphics. So if you were to go into defines, you'll see those that can be uncommented there. Volume force and interactive graphics. Now, hopefully, I'm not forgetting anything there. But let's give it a try. Let's try.
Yeah. In the defines, you need to disable this benchmark also.
Yes. So I commented out the benchmark.
Great.
I've enabled volume force and interactive graphics. Can I drag the? Hang on. This is all great, but it needs to lodge in the right window.
Mm-hmm.
I forget how to. One moment.
It starts it on the primary monitor.
Yes. Do you remember the hotkey? This is embarrassing. Do you remember is it Windows left or Windows right to move it? Because it is full screened.
I guess you have to set in Windows settings the primary monitor to the recorded monitor.
There should be a way there. Windows and Shift there. Let's try that. No.
I think there's also a way to manually override the offset coordinates for the window on screen.
Okay. Well,
it's a bit fiddly.
Windows. There we go. Right. Windows Shift was it. So we have a cylinder here, and I'm gonna. What would you recommend as sort of viewing settings, Moritz?
You can try the default that is on the sample setup script. By default should be you see flag lattice and you see Q criterion. The Q criterion doesn't show anything so far because there's not yet flow going on.
It will start now. Yeah, one sec. Let me do this.
Yeah, here we go.
There you go. Right, that should be running, and I'm back, and hopefully you could all see that. So we have, we can turn on different sort of view settings. So the default, I think, is you just have the vortex isosurface. Is that right?
Yeah, that is Q criterion isosurface. It makes the most boring flow pattern look super fancy. So it calculates the local shear rate and makes an isosurface. It draws an isosurface over where the shear rate is higher or larger, is larger or smaller, and then it colorizes this isosurface by the local velocity. So you get the fancy rainbow worms.
Fancy rainbow worms, I like it. Yeah, if you're not familiar with isosurfaces or whatever, I guess we will mention them. I think you have some in your slides, but yes, a very nice rainbow worms, if nothing else. But I personally, I like the velocity sort of. I guess what would you call it? It's not. It's just a 3D plot, I suppose. So the velocity field.
Ray trace-based rendering, you mean? Yeah, this one.
Yeah, the.
I experimented a lot with different rendering approaches, and this was the ray tracing based velocity visualization was actually brought up by one of my users. He had the idea to do it, and then I was experimenting myself with it a little bit. So this is actually doing volumetric ray tracing. So it shoots rays out of the camera, and they intersect through all of the grid cells, and along the rays, the velocities are probed, and then the color is determined based on different weightings.
Yeah. So to get this up, if you again, it's not like the one thing. I'll give you a bug report now, Moritz. Because I'm doing it on a second monitor where I'm streaming. My mouse though is stuck on the first monitor, so this is something you might, if you ever have time, this is something you might want to look at. But I know it's a very edge case.
Yeah, when the mouse is outside of the primary monitor. But what you can do is if you click once on the screen so that you really see your mouse pointer, you can control the rotation as long as the window is in focus with I, J, K, L keys.
Yes, and it was as well, I believe, right? But I need, it's a. Am I in? Yeah, it's not. Okay, we'll play around with that. But anyway, very nice code. And the point is that this is, if I get it to work again, this is working and calculating this stuff in real time.
What hardware do you have?
Hang on a second. I am messing up here. There we go. So I have a pretty old machine, to be honest. As in, I have is it 3060, I think. So nothing too impressive, I must admit. But it is working then in real time. Oh, one moment here. Right.
If you're working off screen with the mouse, then just click once in the window so that it disengages the mouse controls.
Yeah, sure.
And then it doesn't rotate around all the time.
I must admit, I haven't tested this with OBS, so and two screens. But anyway, that was, to be clear, streaming aside, that was a live, Lattice Boltzmann method simulation of fluid flowing. Controls aside, try it. All you have to do, just to remind you, I just uncommented one little test case here in the setup.cpp file, which you'll find if you pull this, and I commented one thing, which is the benchmark, and uncommented a couple others, and it's all ready to go. So that's that's the code. We'll talk a lot more about it. Shall I jump into your slides and we can get to know you properly, Moritz? So,
Yeah, sure.
I'll jump in the slide, the slides about who you are. So, so you're self-taught. That's very interesting. And
yeah, let me bring up the slide on my side,
Yeah.
because I'm seeing the slides in the live stream only with like a 1 minute delay. Okay, so on my introductory slide, so I have on the right side a bit the formal career that I did. So Abitur 2015, did a Bachelor of Science in Physics in 2018, Master of Science in Physics in 2019. I squeezed it into 1 year. The regular time for a study for doing a master's in Germany in physics is 2 years, and I managed to squeeze it into only 1 year. That was it was kind of insane. But it was working out in the end.
So is that a master's by research, or how do they have a? Did you have a research project, or was it purely kind of based on studies, as it were?
Yeah, and physics. So for the physicists, it was more like a crash course biology, and for the biologists, the other way around. And I was also in the DLR graduate program. That is the graduate program from the German Aerospace Center. That was mostly for networking and doing soft skill seminars with other participants there. So yeah, and in my bachelor, I first came into contact with Lattice Boltzmann. In my work group, we did blood flow simulations back in the day. The very interesting and important application of fluid dynamics, because there's various nasty diseases regarding blood flow. And a particular one that others in my work group were investigating was sickle cell disease. So we were using Lattice Boltzmann as a model for the fluid flow, and then had various models for the red blood cell membranes to get the physics right of the shear and bending forces. And yeah, when the membranes of the red blood cells are defect or have different bending moduluses, then you get very nasty diseases, for example. And in my bachelor thesis, I was implementing a way to have the viscosity contrast properly modeled. So the blood plasma is less viscous than the hemoglobin solution that is inside of the red blood cells. And that affects their deformation in flow and deformation characteristics, which in turn, when they go through very small vesicles, affects the way the oxygen can diffuse through the vesicle walls. And yeah, with the viscosity contrast model, I could match, I could make these Lattice Boltzmann simulations match more closely what provided. So it was a more accurate representation of what was actually going on.
No, that's
and
cool.
Yeah, back in the day, we were working with Espresso. That's an open source Lattice Boltzmann code, and it's a great code. But a lot of PhD students before my time have worked on it and implemented like the membrane model for the red blood cells and various other extensions for it. And it wasn't quite optimized because the membrane model was running on CPU and this is Boltzmann part on GPU, and it had to move around the data every time over PCI Express bus. It was super slow and very painful to run those simulations. It just took forever. So that was one of my motivations to start my own code and see if I can implement a Lattice Boltzmann any faster. And that's what I did. That is how FluidX3D became a thing. I just implemented the Lattice Boltzmann from the ground up in OpenCL. And within a few months, I I had also ported over the blood cell model directly on the GPU, and it was like 20 times faster on the same hardware, just by eliminating this PCI Express transfer that the other software was doing.
Okay,
So,
well,
yeah, and then in my masters, I simulation. The density contrast is 1,000 to 1. So in a lot of cases, what the air does doesn't really matter. So I skipped it at the time. And then I had this tool on hand to do splashing simulations, and that's what I used as a tool in my PhD to study microplastic transfer across the water-air interface by impacting raindrops. Yeah, so that was the formal side, and the informal side was just teaching myself programming on various projects. The first one was an N-body simulator. I started in Java back in school, and one of the very first things that I implemented was some sort of graphic representation of what the code was actually doing, because I hated when software was a black box, and it was just so much easier to see directly on the screen if something isn't working or if it's working the correct way. And for that project, I could see like the orbits of planets around the sun and the orbits of moons around the planets, and all of that in real time. So I built up real-time graphics there from the very beginning, and then later I transitioned from Java to C++ for the for more control over memory mostly, because in Java you can't manually free memory again. You have to wait for the so-called garbage collector, and whenever that kicks in, then you have a hang in the real-time graphics. So it hangs for a bit until it frees the memory again. And in C++, you have just a lot more manual control. And then I bought my first OpenCL capable laptop, and I started also OpenCL development. Yeah.
Yeah, no, that's quite the career path already. So certainly someone to watch. Self-taught and already with a very impressive code out. Should we step on then and talk about OpenCL? I think that's your...
Yeah.
Or should we, well, okay, there's a couple of slides you have pulling the... Yeah, go
on. Back in the day, I had the choice, what do I do for GPU programming? And there was CUDA, and there was the lesser known OpenCL. And CUDA back then, so it was... around 2015, 2016, CUDA back then was a big thing already. And I tried it on my laptop. It was a GeForce 960M, so like a multimedia GPU, not too capable. I could game a little bit, but it was CUDA capable. And I tried to get CUDA running in the Visual Studio, and it just didn't work. So then I tried OpenCL, it worked. And I stuck with OpenCL ever since. And the longer I worked with OpenCL, the more of the advantages I learned about it. And I was very glad that I decided for OpenCL early on. It was a fortunate decision. And so the big advantage of and every CPU that has been built into the last 50 OpenCL capable. I think they came out in 2007, 2008, and they had the hardware to do all of the acceleration, and NVIDIA only like afterwards enabled CUDA and OpenCL on those GPUs. So it works on super old hardware already. And it doesn't matter if it's gaming GPUs or workstation or the same code can run on CPUs as well. So there's cases where the VRAM of the GPU is not sufficient, but the memory capacity on the CPU often is larger. So there's always the flexibility to run simulation. supported, although I don't really have too much experience with those. Regarding performance, there was rumors for the longest time that CUDA would be superior to OpenCL, but that never was true. In the end, they are equally fast. So with OpenCL, if you really optimize it to the max, you can get 100% roofline efficiency.
Well,
and you just can't beat it with CUDA.
I mean, I think that's a very contentious statement, but I think some, certainly the big Gen AI researchers at the moment, where it's all CUDA, they seem to believe strongly, specifically in CUDA.
Algorithms are really favorable for GPUs, and some aren't. But for simple things like a Lattice Boltzmann in the ones that pull streaming algorithm, you can get really 100% on a few GPUs. Not on all of them, but on some.
Okay. Well, yeah. Anyway, but it's certainly the portability. So, You've got a nice sort of splash screen of FluidX3D with the jet there. So yeah, obviously very capable. What did I want to say? An OpenCL is portable, but how well does it work with multiple GPUs? Can you really beat CUDA's sort of all their NVLink and porting things between different GPUs? Now we'll talk about that more, but can you comment on that briefly?
So for now, it's a bit difficult because NVIDIA keep back their NVLink to CUDA only. And peer-to-peer copy, so directly copying data from one GPU's VRAM into the other's GPU VRAM, is not possible through OpenCL currently, because NVIDIA just keeps it proprietary to CUDA. But there is ways around it, actually. So there is POCL, the portable OpenCL implementation, and that can compile OpenCL code to a CUDA backend, and that works with the peer-to-peer commands from the NVIDIA driver, and then you can make it work. And in this case, like, the POCL backend is like 3 times faster than NVIDIA's own compiler.
Okay. Well, okay. So let me flip to your slides that are talking about OpenCL then. So let's go into a bit more detail. Certainly, if you're studying GPUs, this should be on your radar. I guess, would it be fair to say, would you agree that it sort of lost popularity a bit, as you said, maybe about mid-2010s?
It has, unfortunately.
But I think it's coming back a little, is it? Or what's your feeling?
Yeah, the story there was that NVIDIA pushed really much for CUDA, and I mean, CUDA is great, but of course it's proprietary to NVIDIA hardware. And a lot of software vendors started with a CUDA first approach, so they implemented all of their stuff in CUDA to work flawlessly on the NVIDIA GPUs, and then only later on, as sort of a back thought, they implemented another version in OpenCL, just porting over the CUDA code to OpenCL so that the AMD GPUs would also be supported, and didn't put as much time into the optimization, and then the OpenCL port wasn't working as well as the original CUDA version, and that spread the rumor that CUDA would be better. And then, of course, other software vendors caught on and saw that CUDA was working better and went with CUDA, and that's the state where we are today, where a lot of software is implemented in CUDA first, and OpenCL and cross-vendor path only is a second thought. And I've been trying to bring back OpenCL just by pushing out my software as a good example that you can do production software with OpenCL. There's a few quirks to it that I had to fix over the years, and a lot of communication also with the hardware vendors to fix bugs in their runtimes. But today OpenCL is in a better state than it has ever been, because of a lot of bug fixes and the the hardware vendors, they are really actively working on OpenCL support and making sure that the bugs get fixed. And it's not like they abandoned it; they are still working on it.
So you're single-handedly sort of lifting up, keeping keeping open.
Yeah.
But genuinely, I do think that it has sort of seen a renaissance. Is my feeling. Obviously, you're much closer to it, but yeah. So you should maybe consider using OpenCL. No, if you already know about GPUs, but I guess if we jump in, then your nice slides here talk a lot more about it to people that maybe aren't aware. So the idea, it's of course compatible, as you can see there, and you heard it here that it has the same performance. At least if you code well, I'm sure if you've really optimized your code as FluidX3D is, then you can get to CUDA. And you have a graph here of your performance. So
yeah, this is just to showcase various hardware that I benchmarked in FluidX3D, and it's a lot of hardware. At the top is all of the data center GPUs. I've marked it a bit with color. So in red is some of the AMD data center GPUs. One of them is the Radeon 7 that has been marketed as a gaming GPU, but actually it's a data center chip with HBM and FP64 capabilities, so I put it up along with the data center GPUs. I don't care about the marketing names. I care about what's under the cooler on the silicon. Yeah, there's the Intel data center GPU Max 1100 that is Ponte Vecchio. Then there's the NVIDIA GPUs from.
I think I'm pointing to.
There's actually there's no Maxwell, no true data center GPUs in the Maxwell generation because none of them can do FP64. So all of the other NVIDIA GPUs are below in this gaming GPU segment. There's of course the AMD Radeon, also the Radeon Pro, the workstation cards for NVIDIA as well, the GeForce, and in the past they called it Quadro, but nowadays it's just RTX like A4000. For the workstation cards, but the gist is that the workstation and the GeForce gaming or Radeon gaming GPUs, they are identical in hardware. The only thing that might differ is that some of the workstation GPUs get double memory capacity and ECC memory, but the hardware chip is identical. So they also have identical performance characteristics, unless in the software you would like artificially throttle it on gaming GPUs, which some commercial software vendors actually do. It is absolutely hilarious. But I'm not doing it, and I'm showcasing here that performance is identical. What matters here is only the memory bandwidth.
So
because FluidX3D Lattice Boltzmann is bandwidth bound. And then at the bottom section, there's some integrated GPUs, also the Apple M1, Apple M2. So the Apple Silicon, they still support OpenCL. You have to remind that Apple invented OpenCL.
Yes.
They created it originally, and nowadays Kronos Group is maintaining it, and Apple have deprecated OpenCL support on their own hardware.
But no, that doesn't surprise me. Apple do, well, yeah, it's well known. They sort of drop their, they start something up and they drop it. But this idea, so is this a marketing thing that they intentionally throttle, like running on a gaming GPU? Is that?
I know the background about it. I've talked with a few contacts from the industry, and the reason is that it sounds stupid. NVIDIA sent them over Quadro GPUs for development and supported the development under
losing.
Of the workstation GPUs, because in the end they are the same hardware. but like 10 times more expensive. And if the software would work on the cheaper GPUs, then no one would buy the expensive stuff. So I guess that there has been a collaboration between NVIDIA and software manufacturers, and then ended up in this unfortunate state.
Okay, well, you're not throttling stuff, so that's the main thing. But anyway, okay, so yeah, you've got a brief intro.
For support, which the modern Quadros don't. They don't. The only cards with FP64 support are the data center ones, the really expensive cards, A100, H100. But they cost like between $10,000 and $40,000, super expensive.
Yeah. So that's for that's for the IT for the Gen AI crowd, is the H100s and so on. But anyway, you've got a basic. I think you're cutting in and out a bit, I'm afraid, Moritz. I'm losing you now and then. I don't know if that. Well, I think that's. But hopefully it's fine. Let's keep that.
Let's continue.
You have a nice, this is kind of back to basics. What is the difference between a CPU, a GPU? Great sort of intro slide. So the point being, I suppose you're saying that the the GPU is really is made.
The CPU and the GPU.
Yeah.
Sorry, you were cutting.
Yes, we're losing Moritz again.
Next to each other, the differences there. So on the CPU, you get fewer very big cores that have a lot of functionality built in, and a very large instruction set and acceleration for all sorts of instructions. And on the GPU, the cores are a lot simpler. They still can.
Well, we're losing.
The same thing, at least within a
Moritz, if we could, sorry, we you keep cutting out. If I could maybe, if I cut off your cam, maybe we're losing you back and forth a lot. If I cut that out. Yeah.
Too much bandwidth here.
Yeah, it's maybe it's being back and forth. Okay, but anyway, so without the Moritz cam, let's try this again. So so the point you're saying is that the GPU is good at doing the same thing many times, or the same instruction many times, single instruction, multiple data. So it's fast, but only if you have the same instruction over and over again. I guess that's what you're saying.
Yes.
Which
there's not a clear border anymore.
Yeah. I teach this to
So the vector extension instructions.
Yeah.
And each CPU core in itself can do the same operation multiple times in its SIMD unit. It's very similar to what the GPU does in the streaming multiprocessor. And the modern CPUs, they have hundreds of cores already. And if you break it down into the SIMD units, they get to comparable floating points throughput, actually, which is kind of crazy. But the main difference today is like less in the core architecture, but more in the memory subsystem. The CPU, they have a usually 3-stage cache hierarchy. Level 1, which is only for every single core, level 2, and a level 3 cache for all of the cores shared. And then, of course, the connection to the DDR memory. And on the GPU, the cache hierarchy is usually shallower. They only have a level 1 and a level 2 cache. The level 1 cache is only for the streaming multiprocessors. And you can actually use it manually in OpenCL with the local or shared memory.
Yeah, I mean, you can also do that on CUDA.
For example, matrix multiplication. And the level 2 cache is used like the traditional CPU level 3 cache for data that is loaded in multiple times to accelerate it. And yeah, on the main memory side, the CPU, they have usually a lot lower memory bandwidth, between 20 and have a lot faster memory, up to like 5 terabytes a second for the data center stuff. But the memory capacity is more limited because for the super fast bandwidth, the memory chips, they have to be in the direct vicinity of the GPU chip on the same circuit board, and the signal lengths, they just can't be any longer, or the data integrity would suffer. And because the physical distance has to be so small, there's just not a lot of space. So the memory capacity on the GPUs is a lot smaller. What they're doing nowadays is stacking the chips vertically. That's what's happening with the HBM chips. They have like 15 layers, I think, already. But at some point, moving the heat out of the lower chips is a problem.
Yeah, I imagine. Yeah, if you've got stacking, I imagine that would get hot. In fact, even just my little graphics card gets hot running just FluidX3D on one GPU. So, which is a sign that it's very well optimized. It must be getting the most out of my card. But okay, so let's and I'll jump to the next slide. You're talking about the PCIe connection. Obviously, memory movement is absolutely key, at least between the host and the device. The host, the CPU, the device. So how do you find that
directly maps to what the hardware has to offer? So on the left side, there's the CPU. It's called the host side. And the CPU has access to its RAM on the host side, and then on the right side it's the device. OpenCL calls it the device, so that is essentially the GPU. But the device can also be the CPU, so you can also dispatch kernels to run on CPU. But for now, let's keep it at
and how do you find so yeah
accessing data?
No, we're still losing, I feel, Moritz.
I guess it's the German bamboo connection.
Yeah, I was just going to say, how do you find, so with OpenCL, of course, you can dispatch kernels to CPU and GPU. How do you find that? Do you find that useful ever?
It's very useful. Because you can decide if you need more memory, then dispatch it on a CPU. If you're fine with smaller memory capacity, dispatch it on the GPU. It gives a lot of flexibility, and in the end, you only have to write the GPU kernels, the OpenCL kernels once, and they just run everywhere.
So that's the big advantage, is you can write the same code for both.
Yeah. And on the GPU side, the OpenCL memory model also has the local memory that is in red, and the private memory. So the local memory is essentially the level 1 cache, and the private memory is the registers. And local is shared across the cores in every compute unit, and the private is only for every single core. And in between, there's a PCI Express interface that is, it has gotten a lot faster with PCIe Gen 5. So I think that's 64 gigabytes a second, which is crazy fast.
But how do you find the
SLI connection?
How do you find the actual latency? I mean, 64 gigs is good, but per second, but
the latency is in the order of 0.1 milliseconds.
Okay, no, that's pretty
so
good.
So you can like send 10,000 times data back and forth in one.
Yeah. Okay. I mean,
cores are doing, but for sending like data for rendering, for example, where you have a target of 60 frames a second, that is plenty fast.
So yeah, you've got an example. I'm just jumping ahead. I mean, let's so this is an example for people of a kernel. So you typically supply you'll typically be working on arrays, so you'll supply a bunch of pointers to arrays as as arguments, and you'll define this one kernel. So those of you who read code, you can see that we're just adding effectively two vectors together, and you might wonder why. If you've never seen any GPU code, you might wonder why we're only doing one single addition. We're saying C element n is equal to A element n plus B element n. That's just one element. But of course, this is going to get executed thousands or tens of thousands of times in parallel by multiple threads. I suppose that's what you're saying, Moritz, yeah?
Basically, like a loop in C++, with the difference that all of the iterations of the loop are executed in parallel and in random order, which means that you can't have dependencies between one iteration and the previous iteration. So all of the loop elements or loop iterations, they have to be completely independent of each other. And but other than that, it's really much very, very similar to a loop. And any loop where you can split it up into individual elements, you can vectorize it and run it. Yeah, and on a CPU with to like chunks, like have one CPU thread work on the first half of the loop iterations and the second thread on the other half. But in OpenCL with vectorization, you really have one GPU thread only working on a single iteration of the loop on a single data element, and it can be in the millions and it can be in the billions, and the GPU scheduler will just handle it fine. It's even better, the more threads you have, the more efficient it will run generally, because you get better saturation of the hardware. All of the streaming multiprocessors can be occupied at the same time.
Yeah, no, it's yeah. So anyway, this is kind of what I would teach to my students. This is, but if you haven't seen this before, that's the broad idea, I suppose, is that you're doing the same function over and over again, billions of times. And you have, if I jump ahead, you have a slide here on memory access. I don't know if you want to talk about that as well. Obviously, memory, very important, getting the memory layout right.
It's not only very important, it's the most important thing of all, because you would think you would use a GPU because it has so many thousands of cores and so much floating point teraflops a second. But in reality, in most cases, the GPU is only faster because the VRAM has higher bandwidth. Because most compute applications, they are memory bandwidth bound, and to get the full memory bandwidth, it is absolutely critical how you align the data in memory. Because GPUs, they do a thing called coalesced memory access. And that happens when the individual threads access consecutive locations in memory. So the thread 0 accesses location 0, thread 1 accesses location 1. And the compiler recognizes that.
Yes.
And turns it into a load for the entire streaming multiprocessor and a coalesced load. And only then you can get the full structure consecutive memory addresses are not accessed by consecutive threads. So array of structures is, for example, you have a 3D vector with components x, y, z. In the structure of arrays, you would have one. And in the array of structures, you group x, y, z for the first element, x, y, z for the second, and so on. But then you don't get coalesced memory access anymore. Also, if you have any like randomized access, for example, through a lookup table, then it's also misaligned access, and you only get a small fraction of the theoretical bandwidth.
I think
So
I think
it's the most important thing to care about the data structure that you're using in memory and make sure that the memory access is efficient.
I mean, I think it's fair to say that this is also true for CPUs. I mean, the way that you'd have, loading to cache in a CPU would also benefit from, effectively coalesced load. I mean, that's what a cache line is, right?
Mm-hmm.
So I think this is a good principle to follow for performance, in any case. So yes, that's definitely very important. And again, just to advertise, the FluidX3D code, if you actually look into it, is obviously highly optimized with regards to memory. So it's a very good example of this. So you talk later about memory. You talk about later about the layout in memory of your various variables, right? If I skip ahead here.
You can skip ahead. So the next slide was just that the performance for coalesced misaligned memory access is different across GPU architectures. The biggest penalty is for misaligned write access.
Okay. And the example of I mean, we can skip the counting operations here. Do you want to talk about
Lattice Boltzmann part?
Yeah, should we skip to the fluid part, or is there anything else you want to say here, Moritz? Are we still losing you? No.
Your connection just dropped out.
Yeah, we keep losing you, I'm afraid. I don't know, at least from my end.
Can you hear me?
Yeah, I can hear you now, just about. No.
Dropping out again.
Yeah. Can we try call you back, Moritz? Is that okay? Try.
Yeah, let me just hang up for a sec. Hi.
Hi again. Let's cross all our fingers and toes. Let's hope, we don't keep dropping out.
Mm-hmm.
Are you okay if I jump onto the actual Lattice Boltzmann stuff?
Let's go ahead and
now,
talk about LDM.
I will just. I'm sorry to interrupt your part. I did just want to interject here, if you don't mind, with a couple of slides. So I did just want to introduce the idea of CFD, perhaps, or just generally fluid modeling. So there's two broad ways you would model a sort of a generic fluid. You could go the kind of grid CFD approach, where what you do is you would break up your fluid. Now here, this is our flow past a cylinder case again, where you'd have, if you've got fluid flowing, you would have a compression on the on one side of the side of the cylinder that hits the flow, and you would have rarefaction, so lower density behind it, of course. And the way you'd compute that is you would solve a bunch of the Navier-Stokes equations, a bunch of differential equations on a bunch of grid points. You'd compute, at the very least, you would compute the velocity and the density of the fluid, which changes. You can have another approach called a smooth particle hydrodynamics, where you would have Rather than having a fluid that sort of fills a volume, you just have a bunch of tiny little. You treat the fluid as like a bunch of little ping pong balls, but they're not really ping pong balls that collide. In that sense, they are sort of these soft, smoothed out ping pong balls. They're not. They kind of don't have a perfect shell. They just feel a weak repulsive force among themselves. And so that's two ways now. The Lattice Boltzmann is more like the left. It's actually not neither one of these exactly, right? It's more like the grid methods. You have a grid in FluidX3D, right?
Mm-hmm.
Uh,
it's exactly like a grid. So
exactly.
It is a grid-based method.
It's a grid-based method, but it's not quite either of these because you're not solving Navier-Stokes exactly or directly. You're kind of indirectly solving them.
Yeah, you're solving the Boltzmann equation, which is equivalent to Navier-Stokes, but it's a little bit different because the discretization is different.
Yeah. So you have a grid, and that's what FluidX3D has. It has a grid. It'll be in 3D. That grid, of course, has to fit on the GPU. You'll talk more about that, I'm sure, Moritz.
Yes.
But so that, yeah, you have to have a grid. You have to have a bunch of different quantities solved at each point. Now, viewers of my channel may be interested, how does this work with a plasma? And firstly, a plasma is a fluid, and so you can use any of these methods, but there's a little catch, which is for a plasma, there are very long-range interactions because you no longer have molecules that are neutral. You have electrons and protons or other ions. So you'll have long-range forces, like, for instance, the magnetic field. So if you had a magnetic field, you would be going for magnetohydrodynamics, which is like the CFD, but you now have a magnetic field at each point as well as a velocity, which may or may not be aligned with each other. There is an approach called particle in cell, which is the plasma version of the smooth particle sort of approach, where you have a bunch of little particles and they all bounce off each other. They all have their own velocity. But you still have to, it's a particle in cell because you still have to track when those particles move, what the magnetic field is and that sort of thing. So that's kind of how plasma differs, but not really hugely. I mean, it's still a fluid. It still works the same way as any other fluid, and so the methods to solve it are the same. The one thing I did want to say is that one thing I don't think you have, and maybe you have plans for this, is adaptive mesh refinement is used for plasma physics studies, certainly for a lot of fluid studies as well. So where if you have a region of interest, you would then refine this 3D mesh or 2D mesh or however many, you would refine that in the regions of interest, and I don't know if you have plans for that, Moritz, or
yeah, it's like the #1 requested feature for FluidX3D, but it is just super difficult to implement this in a vectorized manner on the GPU, and it's a multi-year effort.
Yeah, this would be a huge, yeah. So you would need like a some sort of octree type deal, right? That you would need to have.
Yes, exactly. The difficulty is that currently, so without mesh refinement, you can do direct grid cell addressing. So the grid cells, they are all stored in a 1D array. But based on the size, the X, Y, and Z size of the cuboid box, from the thread index alone at which coordinate you are in 3D on the grid. And from this coordinate, you can also figure out the direct neighboring grid cells, just with a bit of arithmetic calculation. And as soon as you have an octree, you need some sort of lookup table to get to the neighbors, and it makes it at first more inefficient because coalesced memory access is then thrown off the table. And it makes it also more difficult to set up the octree, especially in a dynamic manner. Like when when you really want dynamic adaptive mesh refining, where defined grid cells are created in regions where there's super tiny vortices dynamically, and then coarsened again whenever a vortex has passed by, and it gets a more boring area of flow again. And the memory management there is really difficult.
Yeah, but so yeah, that's a sort of plus and minus. Of course, the win there would be that you can de-refine the boring areas, right? You would win, in terms of in terms of de-refining, but yeah, it's computationally and in terms of implementation as well must be a complete nightmare. So I don't blame you for this, but this would be the biggest sort of next step. But okay, let's flip back. So with that in mind, with that very basic idea in mind, let's flip back to your slides. So the Lattice Boltzmann method. You've got some very nice diagrams of it here.
Yeah, so I've put up the entire Lattice Boltzmann algorithm as the equations. That is all there is to Lattice Boltzmann in terms of equations. So it is 2 steps. There's the streaming and the collision. In the streaming, it is just loading numbers, loading floating point numbers from memory and storing them in memory again. And in the collision, it is computing actually the density, which is directly proportional to the pressure as it's isothermal, and the velocity of every grid cell just by summation of these so-called density distributions, these f with the lowercase I. And from the density and velocity, you can compute the equilibrium distribution functions. And they are fed into a collision operator, and then it gives you the output density distribution functions that are then put in a stream to the neighboring cells again. So it's always streaming and collision in alternative order. And here I've marked in boxes the stuff that has to be stored in memory. So the density distribution functions, they need to be in memory. The density and the velocity also, because that is what you want to figure out from the simulation, like the results. And then there's also flags, because a grid cell can be like either a fluid grid cell, so there's fluid flowing inside, or it can be a boundary cell of a solid material that the fluid has to go around. Or it can be like a fluid or interface or gas states for extensions. And these density distribution functions, this is the diagram on the top right in rainbow colors where they are located on the grid. So in the middle, this is like when they are loaded into memory and then collided and stored in memory again. And for the streaming step in the beginning, they are loaded from the neighboring grid cells and then streamed inward. There's also the symmetric opposite variant where you start with them in the middle and then stream them outwards. It's called the push scheme. Here what I show is the pull scheme. Okay. And this is the 2D discretization. So in 2 dimensions, you have 9 of these density distribution functions per grid cell. So 1 for the center cell and 8 for the surrounding cells. In 3D, there's various discretization schemes. The most common one is the D3Q19, because that is reasonably accurate, and it also has a reasonable memory footprint, because all of those density distribution functions, they have to be stored in memory, and the more of them you have, the higher is the memory footprint. So for the D3Q27, where you also have the DDFs for the corner cells, it just blows up the memory footprint, and it's not too much more accurate overall.
So, and I think you have these as within the code. I mean, you have these as flags that you can switch between them, or is it hard coded?
Yeah. I've made it configurable. Okay. You can switch between D3Q15 up to D3Q27 if you really need it. But D3Q19 is the default. So I've implemented all of them.
That's really cool. Yeah. Okay. Great. So you can see, if those of you who pull this off GitHub, have a look. There is a switch. Okay. So it's fairly simple, but yeah, as you say, it's kind of memory bound.
Yeah, that is the big problem.
Yeah, because you really can't avoid that with fluids and with a 3D grid, right?
Yes, in the end, it is a data problem, because for every grid cell you find out the density and the velocity. So you have some data for every grid cell, and if you want to resolve fluid flow in high detail, in 3D it goes into the billions with the grid cells, and the memory footprint just totally blows up. And that was the big thing that I got under control finally in my PhD research, optimizing Lattice Boltzmann for smaller memory footprint. So here I'm not sure if we're already on the next slide.
No, I can go. I can go. You want to talk about the bytes and the?
Yeah.
Let's go.
Let's
Yeah,
go to
that's
counting
great.
the bytes.
Yeah, great. Let's do it.
Yeah, so here on the right, I have visualized how many bytes every grid cell needs in memory, and for traditional Lattice Boltzmann with FP64, so with double precision, this is 344 bytes for every grid cell, and this means in 1 gigabyte of video memory you fit 3 million cells, and that's it. And the colors here represent what they actually are. So there's 8 bytes for the density, one double precision number, 3 numbers for the velocity in x, y, and z coordinates, and there's the flex, and all of the gray part is those density distribution functions, and there's a lot of them, and they take up the majority of the memory, but they are not direct observables. You're only interested in density and velocity, but Lattice Boltzmann needs the DDFs to function. They are essential. So what I did was I reduced the memory footprint, especially for the DDFs. So I started already with only FP32, so only single precision floating point. And there's not really a trade-off, because the accuracy is still the same, except for some corner cases, like super low velocity, which doesn't even make sense anymore to simulate. Double precision still has the advantage, but single precision is good for pretty much all cases. And that already cuts the footprint in half. And in my PhD, I reduced it even further by another 3 times to only 55 bytes per grid cell. By reducing the size of the density distribution functions with a streaming pattern and FP16 memory compression. So if you go to the next slide, that is the esoteric pull in-place streaming scheme. So the idea is that traditionally you need 2 copies of the density distribution functions in memory, which is even worse. And the 2 copies are required because there's data dependencies between neighboring grid cells. And if you imagine all of the grid cells get updated at the same time, but in a slightly random order. So if you override one grid cell, but then the neighboring grid cell tries to read what is the value of its neighbor, has it been updated or has it not been updated before? So you get so-called race conditions and random output that is broken. And to resolve that, traditionally you need just 2 copies in memory. So in the even time steps, you read from the copy A and write to copy B, and in the odd time steps it goes the other way around. And with a very clever streaming pattern in Lattice Boltzmann, you can avoid it and resolve it, and only have a single copy in memory. So that cuts the footprint almost in half.
That's interesting.
If you go to the next slide, there actually has been a solution for this so-called in-place streaming that gets rid of the copy, and that is the esoteric twist scheme, which is very ingenious. It shifts the density distribution functions by half of a grid cell into an intricate memory read and write pattern. And the pattern is different for even in odd time steps, but within each time step, it loads and stores in the very same locations, but with swapped numbers. The trouble with this is that it is difficult to implement. And by implementing esoteric twist myself, I found out by accident there's a way to do it in a much simpler way, and that is the esoteric pull scheme at the bottom. it looks very similar, except there's one diagonal, the pink and the green distribution functions, they are shifted down by one cell. And they now are actually in the proper location that is matching between the streaming direction and the neighbor direction. And that makes the implementation a lot simpler. It goes from having to manually implement the indices to doing it in a simple loop in like 15 lines of code. And it's even beneficial for coalesced memory access because the density distribution functions that are stored locally for the local cell, they get coalesced access. The ones that are loaded or stored for the neighbors, they only get partially misaligned access. So it's the optimal memory layout for the in-place streaming schemes.
Yeah, I need to read that. I feel like I need to read your paper to fully get my hand around this. This is quite a head scratcher.
Yeah, it is.
But I'm sure it must be in the code. So yeah, there's probably a place to look that up. But yeah, that seems so. Just to sum up, this is you want to avoid overwriting. You'd want to have grid A and grid B, where grid B is the output, the grid A is the input. And obviously, you don't want to overwrite grid A until all of your threads have done the operation, right? So this
Exactly.
and this avoids that. But yeah, I get what you're trying to do, but I'm still scratching my head. Maybe this is one to read the paper for exactly how you're avoiding. But okay, but that's very clever anyway. I mean, the result. We have a saying, the proof of the pudding is in the eating. So the only thing you care about the pudding, the dessert, is when you eat it, that it tastes nice. And here, the only thing you care about, I suppose, is that you have cut the memory usage in half, or nearly in half, which is quite an achievement. So yeah, that's great. But maybe one to kind of read in detail because it's.
The gist is that every single GPU thread reads and writes only the exact same memory locations in one time step, but with swapping the distribution functions for every direction, and that resolves the data dependency.
Okay.
Yeah, if you go to the next slide, part 2 of reducing the memory footprint. The density distribution functions, usually they're stored in either FP64 or FP32 in memory. So here I've visualized it, how they are grouped, how the bytes are grouped together into floating point numbers. And what I did is I compressed them into 16-bit memory. And this works on literally every hardware because I don't do any arithmetic in FP16. I just convert before I write the data in memory. I convert from FP2 to FP32 to FP16, write to memory, then read from memory again and decompress again. So it's using it only for the memory storage. And all of the modern GPUs, they can do this conversion actually in hardware, which is very, very fast. It takes like one clock cycle to do it.
So is that's always something I've wondered. How fast is type casting actually? So it's one clock cycle, you're saying, for floating points. What about integer to floating point casting? I've never actually.
It's also in the order of one clock cycle. It's a bit different for different architectures, but it's very fast, the typecasting.
Okay. Yeah.
It's usually done in the data port as part of move operations. The move operations, they can copy data around in registers, and in the same clock cycle also convert the data type. So yeah. The compression to FP16, it's funny that old GPUs that don't even have arithmetic support for FP16, they support the conversion in hardware. But to make it work, it wasn't that easy because the IEEE FP16 format is not really suitable for it out of the box. If you go to the next slide, I've illustrated it there. So here on the left side is the native implementation of Lattice Boltzmann. Right. And I've made a plot to look where are the density distribution functions numerically, what numbers are they actually storing.
Okay.
And they are clustered around the lattice Boltzmann weights, which is like 1/3, 1/18, and so they're not nicely centered, but they're clustered around the weights. And there's a modification to Lattice Boltzmann in a paper from the year 1993, before my time. And someone found out that you can do a shifting of those density distribution functions by subtracting basically the LBM weights, and then numerically they are all nicely centered around 0 with very small modification to the algorithm. And the physics of it is in the end the same. It's just numerically nicer values. And with this shifting for the density distribution function, it makes the number conversion work a lot better, because floating point numbers, they are most accurate for small numbers around 1, or alternatively, that's what I did, to shift the range from like plus minus 65,000 down to plus minus 2 for the FP60 formats.
So I'm going to say it now. I was always going to say this. So we discussed this earlier before we started. So I have a video out called "Why OOP is Slow and a Stupid Idea to Fix That." I don't suggest you necessarily watch that, but you know what frustrated me was how many people said that performance doesn't matter. And here we are, and accuracy doesn't matter. And here we are. This is the level. This is some, you know, this is the finest sort of the finest wine, the most aged, sort of beautiful in terms of writing code and optimizing it. This is a beauty to behold, that you've actually plotted the. I mean, I presume you've done this PDF for your own. For FluidX3D, you've looked at the distribution of the floats that you have. So this is the level of detail you go to if you want to optimize your code for everyone out there. Performance matters, and here is the level of detail. This is a chef's kiss. This is beauty. I can't say this is something I'm going to go and do to my own codes, to look at to look at the PDF of the actual, I guess the values, the variables take. This must have been a big sort of, must have been a big job to get these statistics out, or how?
Not really. I mean, I could just allocate the buffer for the density distribution function on GPU and CPU, and then just copy over PCI Express and dump them out into a file.
Yeah, fair enough.
Plot it as a histogram.
But this is this.
But you would wonder, this isn't even the pinnacle of this arithmetic optimization. So you have to remind yourself that a floating point arithmetic is not infinitely precise, and the precision depends on what numerical value the number actually has, and also on the order of operations. And you see here in the collision operator this green mark +1. It matters to add this 1 last. So to do the summation first and add the 1 last, because otherwise you start at 1 and add tiny numbers to a to a big number, and then you get an effect called digit extinction. So it eliminates all of the least significant bits in the mantissa of the floating point addition, and you lose a lot of precision. And if you do the summation of all of those small numbers at first and then add the 1, it's a lot more precise. So there's a lot of optimization that is not directly visible to the eye in just ordering the number of operations in the code.
Yeah, like I said, this is absolutely chef's kiss. This is beautiful. Just you'd think 1 plus x and x plus 1, it should be the same, but this is really great. Yeah, I wonder actually if you've seen this probably has been obsoleted by hardware, but there's something called the Kahan addition scheme. This was from the 60s. This was a way that you can extend effectively for any given FP size. You can extend. You have a little overflow like you'll have two floating point numbers, and you'll have a little secondary temporary variable to store the overflow. That may have been obsoleted now, but as I say, I saw this in a paper from the 60s where you could store that overflow. You could store the this higher precision temporarily. So maybe that's something that's still relevant. Maybe it isn't. But okay, I think it's a similar.
Yeah, the hardware doesn't really support it anymore.
Okay, maybe not. Yeah. Okay, but anyway, yeah, this is good. So is the next slide, is that even more in-depth optimization?
Not really. The next slide is just to make clear that I have decoupled arithmetic precision and memory precision. So all of the math is done in FP32 and the memory storage in either FP32 or FP16, and in between there's conversion.
Okay, cool.
But the slide after that gets into a lot of detail.
Right.
The floating point and posit formats.
Okay. Yeah. Okay.
So there's a lot to how you represent the numbers in memory, to what precision you can get out of it. And there's a gazillion variants of floating point or number representation. And I've visualized them here on the left. So the top is FP32. So you see you have FP64. So you have 64 zeros and ones. They are grouped into one sign bit, 11 exponent bits, and 52 mantissa bits. Below that, FP32, and then various FP16 formats. And below that, there's posit formats. So posits, they do not have a fixed exponent and mantissa size, but the boundary between exponent and mantissa is shifted depending on the numerical value. It sounds a bit insane, but with the diagram on the right, it's a bit easier to explain. For any given number, the precision is actually not the same. Here, the y-axis is the precision in decimal digits, and the x-axis is like what number is represented. And on the top is FP32 in this range from like 10 to the power of minus 16 to 10 to the power of 8. The precision for FP32 is always the same. But for the FP16 formats, it's not. So if you look at the green one, the bright green, this is the shifted format that I'm using. So you have a certain range where you get like 3.5 digits, and then towards small numbers from 10 to the power of minus 8 to 10 to the power of minus 12, it goes down. This is the so-called denormalized range. And by default, the IEEE format is the yellow curve. It's a bit behind the other curves. It's just a green curve, but shifted to the right. And for the Lattice Boltzmann application, you don't need all of these super large numbers. The standard format goes up to 65,000, but the largest possible number that you can get for the density distribution functions is like plus minus 1. And I did a safety range of plus minus 2 just to be sure. So I can shift the entire thing down, which means that for tiny numbers, I can still represent them accurately. And then what I did is this blue one here is the FP16C. This is a custom FP16 format where I stole 1 bit from the exponent and enlarged the mantissa by 1 bit. This gives me a bit more precision, but it shortens the range. On the right side in the diagram, you can see that the range is smaller. For the normalized part where you have high precision, it's actually cut in half, but the denormalized range is still the same. And it is 1 tick above the green curve, so you get a little bit more precision out of it. And to the posits are those pyramids, like the turquoise color and the dark red one. They look like pyramids. Special thing is they work like denormalized numbers, but stretched out to the lower end, but to the high end as well. So posits are most accurate around plus minus 1, but the larger or the smaller the number gets, the more precision you lose. And in general, with 32 bits or even 64 bits available, posits for scientific compute are far, far superior to floating point. And it's unfortunate that computing hardware went with floating point once you see the benefits of posit. Because in scientific compute, you can control which number range you're working with. And if you know that your software works with numbers in the range of around 1, then posit just has so much more precision than in the same bits than the floating point could offer you. And the range towards large and small numbers, so you can represent a lot larger and a lot smaller numbers with posits that would be like out of bounds for floating point already. But in the large and small range, you lose off precision, so it's a bit of a trade-off there. And in the production version of FluidX3D, I went only with the IEEE, so with the shifted FP16 format and with this FP16C format, because with only 16 bits available with posits, there's diminishing returns in this particular application. I tried it, but the floating point they just work better. And yeah, the FP16C format, if you go ahead to the following slide, the trouble there is that for this custom format, there's no hardware conversions anymore. So I had to write my own conversion functions. And this gets down to a lot of bit manipulation, bit shifting, and to also have still the normalized and the denormalized ranges, because especially denormalized numbers are absolutely critical. And I wanted to get it as fast as possible, and all of the existing solutions for the conversion were non-satisfactory. So I did my own and made it non-branching, so there's not a single if-else in there.
Okay.
And super fast.
So the long and short of these two slides, Moritz, is basically when I need some very very lean, very thin in memory approach, what I'm going to do is I'm going to go into FluidX3D and I'm going to steal whatever it is you have there, because this looks like it's been a lot of work, and you've obviously put a lot of work into this and have benchmarked it and optimized it. So it's an open source code, right? So I could go in and steal it.
It's actually not open source. I have to correct you. It's source available.
Yes, okay. It's
there's a small difference. So I exclude military use and commercial use.
Okay.
And that makes it not compatible with the open source definition anymore. So it's formally source available.
Fair enough. So for my, I just do science. So for my it's non-military and non-commercial, I will.
I encourage academic use.
Yes. So for anyone else watching, this is kind of, as I say, this is the level of detail you really need to go into to make your code really super efficient, and this is quite a a thing of beauty to see. Very, very interesting. Very interesting. I'm kind of blown away.
The 16-bit memory compression, it reduces the memory footprint almost in half, and it has a second benefit. In every time step, you can load twice the number of grid cells per given time, because they like two grid cells fit in the same memory space, which means it makes it also almost twice as fast.
Okay. Yeah. Yeah, I mean,
in the following slides, I have some examples of comparing the different floating point decisions.
Yeah, so the Kalman vortex, yeah.
Yeah, the Kalman vortex here between FP64 and FP32, there's absolutely no difference. It looks identical. And for the IEEE FP16, you see some artifacts as well as for the FP16S. And what this visualizes here is the vorticity, which is a finite difference of the velocity in neighboring grid cells. And if you can imagine, when you store the density distribution function, the sum of them is the velocity, and that gets stored in lower precision. And if you make a finite difference between velocities in neighboring grid cells, you will get digit extinction, and you will see at some point you will see artifacts earlier. And I've like overexposed the range of vorticity. It's like a very much overexposed image, so that you can also see the fine detail for small numbers. And there it finally becomes visible that there's some discretization artifacts for the FP16S and also the IEEE FP16. And the FP16C, it starts to mitigate those finite difference effects because you get one more bit in precision. It cuts the truncation error in half. And this is like one of the nice showcases that where this extra bit in the mantissa actually makes a little bit of a difference. In terms of like total accuracy of the simulation, this is the bottom chart. I've put in the center of the box a point and check like what is the left-right component of velocity over time. And every time clockwise or counterclockwise vortex moves over this probe point, you see the line squiggle up or down in the bottom plot. And I simulated this for like 50 vortices up and down, and then for the 50th one, I've enlarged it and really spread it out. And after 50 vortices, all of the lines are pretty much still on top of each other. Only there's a little bit of discrepancy with the FP16S, a little bit of phase shift, but it's still super accurate. And it doesn't really make a difference in terms of results compared to the full FP64 precision.
No, so to be fair, and speaking from, wearing my plasma physicist hat, this, for plasma physics, you probably would want something like the full, at least the full FP32 everywhere, because so vorticity would be the curl of the velocity, right? So any sort of derivatives, certainly for plasma physics,
amplify the errors.
Yeah. So
especially if you have third or even fourth derivatives.
Well, probably not the fourth order.
For the bending models, sorry, for red blood cell membranes, there's bending models, and they need the fourth derivative of some quantity. You can imagine what a nightmare this is.
Yeah. Okay. So maybe not that far, but you would need, as I mentioned, for all the electromagnetism, you'd need derivatives. So fair enough, but to me, it's still really cool that that we have the option there, and it obviously reduces the memory footprint by a lot. So yeah, that's very, very neat, very cool. And once again,
you can
all of these you can check. Sorry, you can just change at compile time, right? There's an option for changing this.
Yes.
Okay. Perfect.
Yes, it's in compile time you can switch the memory position, and as you demonstrated at the very beginning of the live stream, clicking the button to compile the software, it's like 5 seconds to compile the entire software.
Yeah, so that's fine. It's compile. There was a question in chat about rotating frames. Do you do or a rotating frame into?
Yeah, it can be a bit emulated with volume force that is like representing the centripetal force. So you can set in FluidX3D with the volume force extension. A volume force is different for every grid cell. For like one example would be like to have a planet with gravitational acceleration towards the center. So this is one of the applications that would work here. But you can also make it like a centripetal acceleration. But it's still not the same thing as a rotating reference frame. If it's like really a rotating, you have to like make the fluid rotate on the grid, because there's different terms that are missed out with only forcing.
Yeah, okay, but that's cool. Should we go on, or did you want to say anything else about the Kalman vortex?
Yeah, you can continue with the next sample briefly. So this lid-driven cavity, This is like a truck, a trailer, a box that is open on the top, and on the top there's like wind moving over it, and um, it's forcing the fluid at the top of the box to move, and then it creates a vortex in the box. And the lines that you see is the cross-sectional velocity profile for the vertical and the horizontal. And for all of the different position levels, the velocity profile is on top of each other.
Okay.
So this is a case where the floating point position really doesn't matter at all. And the discretization errors from the Lattice Boltzmann grid discretization is like the largest error contribution.
Okay. Yeah, cool.
Yeah, and then I guess the next slide is multi-GPU. We wanted to touch that again.
I mean, very briefly, maybe. I'll get myself out once again. If there's anything else you want to talk about multi GPUs.
Yeah. So I mentioned that in OpenCL it's not possible to do a peer-to-peer memory copy. So you have to copy all of the memory into system RAM and back out of system RAM. And that is the scheme that I implemented in FluidX3D. Within system RAM, it only does a pointer swap. So it makes it reasonably efficient. And the big benefit here is that it works cross-vendor. So you can pair an NVIDIA GPU with an AMD GPU and an Intel GPU, and they can like be in quotes SLI together and pool all of their VRAM for a big simulation. It doesn't matter from which vendor the hardware is. They all work together seamlessly with this.
And it would have to do this every time step, of course, right?
Yes, and in every time step, it extracts like this cuts the simulation box in like two parts, and where they touch, there's an interface, and some data is to be transferred across the interface in every time step. So the entire box is like 10 gigabytes in size, and this interface area is like 10 megabytes. That is this transfer buffer that gets extracted first within VRAM and then copied over PCI Express twice.
So this is something as well that kind of is a feature, I suppose, gets a bit harder maybe with AMR, but knowing how to divvy up your domain is quite if you see what I mean, knowing how to cut up your domain. If you had like 16 GPUs, knowing which part of your domain to put on which GPU can be quite a challenge sometimes. I think.
I implemented this that you as a user in the setup script in the LVM constructor, you decide how you divide the grid into domains within X, Y, and Z direction. So you can have like 2 times 4 times 3 boxes, and the product of domains is the number of GPUs that you need. And when you run it, if there is enough GPUs of the same name, they will automatically get assigned to the domains, or you can also manually specify a list of GPUs if they are unequal GPUs. So say you want to run it on a GPU with ID 0, 5, 6, and 7, and you can specify it for 4 domains and they will get assigned.
Okay, that's interesting. Yeah, a lot to I guess that's very involved. A lot you've got to really look into it.
I've hidden away most of the complexity. So as a user, you only specify you want this many domains, and you specify you want to run it on those GPUs, and it assigns it automatically.
Okay. Shall we go on then? This is about the queuing kernels.
Yeah. So when I first experimented with multi-GPU, so within a single node, you could run multiple threads to enqueue the different kernels, but the enqueuing is non-blocking. So one enqueue command, it instantly finishes and goes to the next. So I can do this all single-threaded on the CPU side within one loop, enqueue all of the kernels for the different GPUs, and then make another loop where I set the barrier to finish all of the kernels, and that is like a synchronization barrier that waits for the last one to finish. And with this, I don't even need OpenMP or multi-threading. So it simplifies it a lot.
Yeah.
And
I was looking NVIDIA recently, well, not too recently, but they made a change in CUDA for how you can launch kernels from within kernels. I can't remember how.
Yeah, some OpenCL devices
Yeah,
also support it. It's a feature
yeah.
of OpenCL 2. There's some AMD GPUs that support it, but it never caught on broadly across the
Okay.
vendors,
Okay. So you
device side and queuing.
you effectively
But I
just
don't even
yeah.
need it here.
Okay. You effectively just queue on the CPU and you're happy with that, right?
Yes.
Okay. Yeah.
Yeah,
No.
it only needs the simplest functionality of OpenCL 1.2, so not
Okay.
even the latest or the newer standards. The 1.2 standard is the most supported one that works everywhere, also still on Apple hardware, and it has all of the bells and whistles that I could ever need.
There's a question in chat. Could you go into some detail about how boundary layers and their detachment is modeled? So the boundary, I suppose, of any object you have.
Yeah, that is a big trouble. I do not have a boundary model
Okay.
implemented. So the trouble is with Cartesian grids that you have the same grid resolution everywhere, and when you have like a flow around an airplane, then there's a lot more detail going on in the so-called turbulent boundary layer that sticks directly to the wings. And further away, you don't need that much detail. Again, you would need adaptive mesh refinement ideally. But there is models to work around it a little bit and allow the boundary layer to be modeled more accurately in even coarse resolution. It's the so-called boundary models, and they work in essentially more like a free slip or friction slip is like one way to do it. So the boundary layer itself acts a bit like a lubrication layer for the air above the rest of the wing, and if you would directly resolve the turbulent boundary layer, you would need microscopic grid cells, and it totally blows up the memory footprint. So it's difficult to do it.
Okay. Yeah.
And
Well.
I've experimented a little bit with boundary models. I wanted to try, as I said, this friction slip or free slip models, and it turned out there is no way still known for Lattice Boltzmann to have a general direction free slip boundary. Like free slip boundaries means that the fluid can go over a boundary without sticking to it, so that the velocity directly on the boundary is not impacted at all. By default, Lattice Boltzmann has a no slip boundary, but the fluid velocity on the boundary is zero, or like matching the boundary velocity. And there is an implementation where you do a specular reflection of the density distribution functions that hit the boundary, but it only works for axis-aligned walls, and it doesn't work for the edge, or rather for the corner case of concave corner distribution functions that like reflect off the corner of a grid cell. And there's no solution out for this in literature. I couldn't find a solution myself, unfortunately. And all of the papers who mention the free slip boundaries, they only implement it for the nice case of axis-aligned walls, like where you have like on one side of the simulation box a mirror, basically.
So, and I guess there's a
So I got a bit stuck with the development here.
I have a broader than question about Lattice Boltzmann specifically. I mean, how compared to the usual Navier-Stokes, how hard is it to sort of extend it? I suppose with, what if you had temperature terms? What if you had, any other sort of forces or something like that? Gravity, maybe.
Yeah. There's a lot of extensions to Lattice Boltzmann, and I've implemented many of them in FluidX3D already.
Okay.
For gravity or volume forces, or they are basically equivalent to a pressure gradient. There's the so-called GUO forcing, so that adds a force term to the collision operator, and that just handles volumetric or force per volume rather. There's an extension to do thermal convection flows. That works by introducing another subgrid with a very coarse discretization of D3Q7 to model thermal distribution functions. And they are coupled to the lattice Boltzmann again over GUO forcing, because in parts where the fluid is hotter, it gets less dense with thermal expansion, and then it creates a buoyancy force, a local buoyancy force, which can create flow again. And the flow in turn moves around hot or cold parts of the fluid. So that's a two-way coupled extension there.
Okay.
And I've already implemented it in FluidX3D, so you can set temperature boundaries, a hot boundary on the left, cold boundary on the right, and then you will get circulation flow.
That's interesting. Okay, no, that's cool. Yeah, yeah, we should try that sort of convection. Yeah, that's cool. Okay, should we move ahead? Your next slide, you're talking about single node model for your domain.
So traditionally, you would implement multi-GPU with MPI, and that is still also the way to go for multiple compute nodes. But MPI tends to make the code a mess, and for now, I've gone with only multi-GPU on a single compute node implementation, and it has some big benefits. Like you don't even need the MPI library, which is not even available on all computers. And the bigger advantage is that with MPI, the domains are not all the same. You have one master domain and a lot of slave domains, and the master domain also needs a master copy of the entire grid. For any, like if you dump the data into files on the hard drive, for example, because with MPI the memory is distributed, could be even distributed across multiple servers, and for any data export or even visualization, you would have to create a big copy of all of it on one machine to assemble it together. And with the single node parallelization, the master copy is assembled on the fly out of all of the domains, and I don't need a separate copy of it in system memory, which reduces the memory footprint for the CPU side.
Okay. Now we've been stringing a while. Should we jump to the visualization part and maybe
let's go to visualization.
Yeah. I'll skip your large CPUs. Let's go to the rendering part. So you do you use something like OpenGL? I mean, I didn't check. Or
no.
you
that's the thing. Rendering with OpenGL is not supported on some of the data center GPUs, and also it is troubling with hardware. So what I did instead was write my own rendering engine from the ground up in OpenCL directly.
Okay,
and that has a benefit that I can do in situ rendering. So I simulate a couple time steps with Lattice Boltzmann, then pause the simulation, and then all of the data is already in the fast video memory.
Yes.
So I can just read out the data from video memory and render it to an image, which is in the end just an integer array, and then send the image to the screen. And that's the only way actually to render those super large simulations, because with billions of grid cells, with post-process rendering, you would have to store volumetric files and volumetric data to the hard drive, and it just blows up hard drive capacity.
Yeah.
And with in situ rendering, you can skip all of that.
Yeah, no, that's very very neat. I mean, this is just because what we taught to our sort of game students is that OpenCL does work with OpenGL quite well, of course. So in principle, of course, you can interface the two quite well. You can just pass a pointer to the to whatever your kernel calculated, and you could render it in principle if you are prepared to. right?
Yeah, the advantage of my approach is that it works when you have a data center GPU, for example, in your system that doesn't even have a display output.
Yeah, okay.
Because then OpenCL renders the image, I can send the image to the CPU, and the CPU over the integrated graphics, for example, can put it out on the monitor for real-time rendering even.
Okay, yeah.
So it just works everywhere under all circumstances.
Okay, yeah, no, that's great. Let's jump into it, I guess. So your next slide, you said, yeah, you're talking about in situ rendering.
Yeah, we can skip the slide. I covered it already.
But can we skip ahead to the marching cubes, because I find that very interesting, and I use that quite often. So if you want to talk about that, that'd be very interesting, I think.
Yeah, marching cubes is a very ingenious algorithm to create isosurfaces on a volumetric grid. A good application is CT scans, for example, where the CT scanner provides also data on a volumetric grid and density values, like bone or metal would have a high density and tissue or air would have a low density. And to render this, what marching cubes does is in between every cube of 8 grid cell, it checks if there's if it's a case where the density value of some grid cells is below a certain threshold and of some grid cells is above a certain threshold, which means that in between those grid cells it has to insert some triangles or a surface. That's the gist of it. And to cover all of the cases with with 8 cube corner points, any one of them could be either inside or outside a given volume. And there's 2 to the power of 8, 256 different cases, and they are covered in a triangle table. So based on which points are inside or outside, you look up in a table some values, and they tell you which combination of triangles to insert and to render, which is very smart. The triangle table itself is kind of huge. In the original implementation by Paul Burke, it was even bigger, as all of the values were stored as integers. I compressed it down a little bit by using the 8-bit char data type, and I also bit-packed every 2 values into a 1 byte, because the range is only from 0 to 11 plus out of bounds case. And there's another table there for the edges, so you can look up in the table for which edges do I even have to interpolate, like on where the vertices of the triangles are located. And I figured out, since the interpolation on the edges is only in 1 dimension, it's faster to just do it for all of the edges instead of looking it up in the table, and that makes it even faster, and it skips the extra table. So it makes the implementation both simpler and faster. And you can see it here on the right side. That is the entire algorithm. The table is like the biggest chunk of it, and the rest is interpolation and then assembling all of the triangles. Okay. And this table in OpenCL, it has to be stored in so-called constant memory space. It's a part of VRAM that is intended for read-only, and the driver can make it cached in level 2 cache for faster access.
Okay, cool. Yeah. That's interesting. Again, something that I may end up pinching from you as if you've, because I've seen in C++ the original one, I believe. But yeah, if you've compressed it, that's certainly a lot faster. Okay. Should we move ahead talking about the ray tracing as well?
Yeah, I can briefly cover it. So the idea of ray tracing is that you physically accurately simulate how light reflects and refracts, in this case through the water surface. And the clever trick for ray tracing is that you go in reverse. Yep. So instead of simulating all of the gazillions of possible light rays that are in a given room, you only shoot the reverse light rays out of the camera, so you only model the rays that will later hit the camera. So you go reverse out of the camera, traverse the in this case a 3D grid. There's a fast algorithm called ray grid traversal. It's even faster than bounding volume hierarchy. So it's a sort of a very fortunate coincidence that the Lattice Boltzmann Cartesian grid already can function as the acceleration structure for ray tracing here. So the grid, it's basically like rasterization. Every grid cell that it touches, it checks if there's an isosurface in there. Again, with matching cubes, it generates the isosurface on the fly. And if it intersects a triangle, then I compute the reflection and the refraction rays with Snell's law. And for the internal refraction rays, I calculate one more reflection out of it, or refraction out of it, and then get the skybox colors and mix them together. This can also be repeated recursively, or like rather in a loop, because OpenCL doesn't really support recursion. But you can repeat it multiple times to have reflections of reflections and so on. And it makes for a really nice visualization of resurface simulations.
Now, with that, I'm just trying to think. So because it's in a kernel, right? That must, if you had one ray which is absorbed immediately, and then you had another ray that reflects like 5 times, surely that would sort of, you'd be running one of the kernels in one of your, let's say, SMs, while the others are effectively finished. So is there much of a performance hit there?
Yes, there is. So you get thread divergence. When one thread immediately, one ray immediately terminates, while another ray just bounces around a lot of times. Then what the GPU does, it has to wait for like the longest running thread to finish, and all of the others have to wait and stay idle, and that way you lose performance. But there's a trick that I use to speed this up. I don't have the slide here, unfortunately. But the trick is essentially to compute rays together that are in the same direction. So on the screen, I take 8 by 8 pixels and compute those rays for this quadratic patch of 8 by 8 pixels in one work group, in one streaming multiprocessor. Because if those rays are in a tight bundle, there's a high probability that all of them will like either terminate directly on some surface or bounce around a bit longer.
Yeah, no, that's very clever.
That speeds it up a lot. The alternative would be like to, instead of 8 by 8 pixel patches, do 1 by 64 pixel stripes. And this is like the naive approach. But in this case, you have like a wide stripe, and then the rays can widely diverge, and you lose performance.
Okay. No, I get what you're saying. So this is the kind of thing that it's like matrix multiplication, let's say, right? If you wanted to do matrix multiplication really efficiently, you would with a very large matrix, you would do 8 by 8 with a single work group, or send that to a streaming multiprocessor.
Yeah, you tile it.
Yeah, exactly. So yeah, if you're familiar with kind of optimizing in CUDA even, or OpenCL, this is, I suppose, quite a common trick. But yeah, no, that's really neat. Yeah, that's good. Okay. I'll jump to the next slide, I suppose.
I have a couple more slides. Like this one is ray grid traversal. This acceleration structure. Basically, it's like rasterization. You shoot the ray through the grid, and every grid cell that it touches, you have to check. But you don't have to check like all of the grid cells for every ray. So only the small subset where the ray is actually passing through. And in the cells that are touched, you check with marching cubes if there is an isosurface, and then if there's an actual intersection between the ray and one of the triangles, and then you compute the intersection point with the Möller-Trombore algorithm, so the ray triangle intersection algorithm. On the next slide, I actually have an older implementation of that that doesn't work for the planar edge case. Like when the ray is in the same plane as the triangle, then it will fail.
Okay.
I fixed it already in the repository. And then the slide after that, this is the normal interpolation. This is a trick to make the reflections look very smooth. So if you just reflect on the triangles, they will look like a diamond ball basically instead of a droplet with flat faces. And since from the ray grid traversal and the matching cubes, I can get the gradient. I can get the curvature and interpolate the curvature and or not the curvature, but I can interpolate the normal vector to the intersection hit point, and then it looks like a very smooth surface.
Isn't this
this is
isn't this Phong shading in I can't remember if it's Phong shading or Giraud shading in regular 3D,
the top one is Phong shading.
Yeah.
Where you have like one normal for every triangle, but the normal is the same for all of the points on the triangle.
No, but isn't Giraud where you do interpolate in 3D in normal kind of polygonal 3D. Maybe I'll look this up after. But
you can do the normal interpolation also for rasterization graphics.
Yeah. Okay, but yeah, no, that's also quite cool. Yeah.
And then the next slide is just this memory load stencil for the normal interpolation for each of the 8 cube corner points for matching cubes. I need another 6 grid sets as a stencil for the finite differences. And in this case, I'm reusing the 8 purple points that I already loaded for matching cubes, so it reduces the memory access. But since this interpolation is only done once the hit point has been found, it is not. It doesn't take too much time.
Yeah.
The most time is spent in the ray grid traversal, and this is only done once per ray, so it's quite fast. And then the last slide for the rendering here is the skybox color. This is just UV mapping, where you load some texture and you convert it to the 2 angles for a vector on a sphere.
Okay. Yeah. No, that's cool. A lot of interesting. You implement that all yourself, which is pretty neat as well. So anyone interested in graphics and the kind of nuts and bolts of how graphics works, I'm sure this is a very very good example of that, or of ray tracing specifically. Okay. Right, so should we get ready to wrap up there? We've been going for a couple hours now.
I guess we can wrap up.
I mean, ultimately, I'll get myself back in here. All I would say is, in summary, you should definitely download this and have a play, have a try running it, and see what you find. That's for sure. And if you are interested in GPU programming, you should definitely look at the implementation. Lots of interesting stuff we've talked about, the mixed precision and how to handle converting between the different precisions, how to handle ray tracing, how to handle Lattice Boltzmann. So very interesting. Thanks a lot for coming on. Are there any other things you'd like to talk about? Anything you'd like to promote besides your code, Moritz?
Yeah, thanks for having me. Of course I want to promote OpenCL because I really think it's a fantastic language, and it only has advantages in the end. It works everywhere. Cross-compatible, can even do a cross-vendor multi-GPU. And GPU programming in general is just really fantastic because the speedups that you can get from GPU vectorization are just absolutely immense. It's like 100x compared to running single-threaded code on the CPU. And you can crack down on a lot of hard computing problems with just brute force GPU power.
And so, kind of, what's next for yourself? What's next for this code, and what's next for OpenCL? Can you tease us with a few other things?
Yeah, so as for OpenCL, in my opinion, it is mostly finished. So it has all of the tools that one could need. There is a few extensions still that are desirable, like, for example, peer-to-peer copy for multi-GPU, or exposed matrix intrinsics, for example. Like if you want to use the tensor cores on NVIDIA GPUs with OpenCL, you can't do it directly because the functions are not exposed in the OpenCL C language, but you can still use it with inline PTX assembly, sort of write wrapper functions around a short part of assembly and use it that way. So it's very flexible. But OpenCL as a standard mostly is finished, and it doesn't have to be changed a lot anymore because it is already a great API and a great tool for programming. The only thing that has to be like continuously worked on is maintenance and fixing bugs in drivers, like whatever users or developers find in the API. It's always great to contact the hardware vendors and make them fix any bugs in the drivers. I did it many times with NVIDIA and also a couple times with Intel. And it's a win-win to report any bugs that you find, because in the end it makes the software work better for you and also work better for everyone else. As for FluidX3D, I don't have like concrete plans on what I want to do in the next time. So during the last months, I've mostly cracked down on all of the remaining bugs that were in the code to enforce my zero bug policy, ideally, until a new of course always until new bugs are found. But currently the number of open known bugs is 0. And I just want to have it work out of the box without any issues on every hardware for everyone on every computer. And it took a lot of effort to get there. And occasionally, always, some people find things, and I'm always happy to fix any bugs. Yeah, I'm looking into adaptive mesh refinement, but no, like I didn't find a good solution for it yet, and it's just experiments, and it's slow going as I only have the weekends for working on the project. Yeah, I'm quite occupied by the daytime job.
Yeah.
So it's always limited time for working on FluidX3D.
Well, cool. Well, thanks a lot for coming on. Once again, I encourage everyone to give it a try. So, yeah, thanks. I'm going to end the stream here, and I will see you all in another video.
Thank you.
Okay, we are now, that's